hopefully we'll get that fixed in a moment. Okay, right. Our in-house tech man has said that it should be okay now, so I'm going to just rewind to start all over again. So hello again, welcome to the second live event for Light Up, the Women in Chemistry project partnered with the Royal Society of Chemistry. Today we've got the same team as last week, minus poor Sophia, who is stuck in the lab dealing with some problematic experiments. But we've still got myself, so if you remember me from last week, I'm Danny. We've also got Nat and Emily and Abby. So last week we spent most of the session answering all of your questions. Those questions were coming through really quickly, thick and fast. So please do make sure that you're posting all of your questions today as well. We want to answer as many of those as possible. And lots of people, a couple of people last week were saying to us, please, can you ask us about the challenge? We want to know more about the challenges. Well, we actually didn't talk about the challenges last week for a reason, because that's what we're going to be talking about today. So just to remind you, hopefully you've all been playing around with the challenges, but just to refresh your memories. So the first challenge that we set you was to make your own camera obscura. That basically just shows you that light can travel in straight lines. And I know that lots of people on our team have had lots of fun making our own camera obscuras and taking some, in my case, slightly awful pictures of the view outside my window. A couple of other members on my team have had much more success with their camera obscuras, and those pictures will be going up on the website very soon. So hopefully you've had fun with that too. The second experiment was the flicker effect of lights. So this is where you should have been taking either someone's mobile phone, either your mobile phone or someone in your family, and then filming LED lights. And what you should have seen is sort of a light passing across the screen, or a black sort of curtain, I guess, going across the screen at a particular rate. And we were just sort of capturing that on our phone and just observing how amazing it is that our phones can capture that, but our eyes can't, and that's happening all the time, but it's so weird that we can't see it. So hopefully you had fun taking little videos of various LED lights around your home. Then the third experiment was to use a laser pen and set up your own diffraction grating. So this quite nicely shows you how we can split light. So hopefully it has quite a rudimentary setup with, I used mine with clothes horse pegs. I think Emily suggested she was going to use blue tack to get the CD to stick up. But it was all good fun in the end, and it worked. When I tried it worked quite nicely. Hopefully it worked quite nicely for you as well, trying it at home. And then the final experiment was to actually investigate different sunscreens in your home using UV beads. So UV beads, the little pack that I bought off eBay, they were totally colourless in the dark, or just in a dark room, like probably the room that I'm sat in right now. But then if I was to leave them out in the sun or expose them to a UV lamp, then they would become coloured. And we were just putting some of the beads in plastic bags, covering the plastic bags with various sunscreens, and testing really by looking at how coloured they became, the varying levels of how well those sunscreens were able to protect against the UV rays. So I think that's a fair summary of all the experiments. So I think what we'll do is, I can see that we're already getting loads of questions through, which is amazing, really, really great, because that's what we would like to spend the rest of the session doing. We're going to try to answer all of your questions about these experiments today. and I'm going to be passing, I'm not the expert on this science, so I'm going to be passing these questions over to my expert team. So yeah, let's get started then. So the first one that's come through is, how different is it to do experiments like this at home compared to doing experiments in the lab? So does anybody want to pick that one up?
I can start if
Yeah, Abby, awesome. Yeah, go for it.
So I guess the underlying principles of doing a practical are the same. You're still getting down and dirty with the experiment, whether you're at home or whether you're in the lab. But I guess the home experiments are a lot safer, and so you don't need to be wearing protective wear. So for us in the lab, if you're using chemicals, you wear a lab coat, goggles, and during COVID times, a mask as well. And so I guess in terms of safety levels, the lab-based experiments can be less safe. I'm not sure that's really the right way to explain it. And I guess the room you're going to be in is going to be a lab that has the facilities to make it safe, like say a fume hood, which allows all fumes to be removed so that you aren't breathing them in. In our case, we're using lasers in a big black box, and that's to protect us from looking at the laser or being in contact with the laser. So there's a lot of differences in terms of safety aspects, but the fact you get to do the underlying principles essentially can be very overlapped. Don't know if anyone else has anything to add.
I suppose I would just...
Yeah, you carry on that.
I would just add that, you know, one of the experiments you did with the laser pen, that is just, it's just a pen. The laser in our labs is, they're very big boxes in a very big table, so the size of the scale of the experiment is completely different as well. Our laser, because it's so much more powerful, it's actually quite big. I mean, we have a whole room with a big table on with lots of boxes, and that's our big laser. So in terms of scale is also different in that sense.
Emily, I remember from one of our talks that we were talking about I was telling you about using the clothes horse pegs to prop up the CD, and you mentioned that actually that is quite similar to sort of the problem solving of making things work in the lab and sort of using what's available to you. That was quite similar. Could you repeat that for the viewers or expand on that?
Yeah, absolutely. So often you'll find in our line of work that scientific equipment can be extremely expensive. So for example, if we wanted a mirror, it can cost hundreds of pounds for one mirror. And so within the lab, you have to be resourceful and use anything you can find to solve a particular problem that you're having. And so one of the problems we were having was making sure that our sample was in the path of our light beam to be able to study its effects. And so we looked into many different ways of solving this problem, but in the end, the best way to do it at the time, we've since moved on and actually developed something a bit more permanent, but at the time the best thing we could find was a couple of elastic bands to hold the sample up in the light beam. And so that was the setup for about 2 or 3 years. They snapped occasionally, but they're easy enough to replace. Yeah, and many other things. So I've been solved with blue tack, for example, if you need to slightly change the height of something. just put a blob of blue tack at the bottom and it's a bit higher. So yeah, I think household objects are underrated in scientific labs. Sometimes you don't need to spend hundreds of pounds on scientific equipment when an elastic band or blue tack will solve the same problem. So yeah, that's a nice link back to the home and the lab as well.
Can I add something there, Danny, if you don't mind?
Yeah, of course. No, go for it.
That reminded me that because I came from university from where Emily and Abby are right now, but I'm working in a company, and they had this this machine that is a solar simulator. It's just a big lamp, but inside, for it not to get very hot, it's got a very powerful fan. And the samples we were putting in were just these squares of just plastic squares were the samples, and the fan was so strong that it was making these plates fly away, which ruins your sample, which is bad. And when I arrived, they're like, oh, how are we going to solve this? And they seemed like very worried about how to solve it. And I was like, don't you have some blue tack? and they're like, oh yeah, we never thought of that. I was like, yeah, just put some blue tack. And so now everyone that uses that machine uses blue tack, because I just put it in the way that literally you just put the plates and you hold them with a bit of blue tack, and it works perfectly well. And so now everyone uses that technique. And yeah, just sometimes it's like Emily was saying, you get so bogged down with using this scientific stuff that you forget that blue tack's just good enough sometimes.
That's amazing. I think that it's really interesting for everyone to know that we are using things like that in the lab alongside, lasers that must cost, how much they cost? Hundreds, thousands, if not more. I don't know how much lasers cost. And that you're using things like blue tack alongside it. It's just a bit mad.
Yeah, a laser system like the ones we have in our labs can go from 200 to 500,000-600,000 pounds. They are expensive. So that's when you set up a laser lab. The laser is the big thing, and you set it up, and you use it for, I think Vaz has had his laser for going on 15 to 20 years, something like that. But it's still working. So.
You would hope so when you spent that much on it, wouldn't you?
Yeah, absolutely.
Amazing. Oh, super. Right, what else have we got coming through? Somebody said, are the laser pens similar to the lasers you work with in the research lab? I think we touched on this a little bit earlier, but does someone want to clarify that?
Yeah, so I'll go
for it.
I was just going to say, we discussed the scale of what we use compared to the laser pen is very, very different, and so is the power that those lasers emit. So there's different what we call classes of lasers that range from class 1, which are the safest ones, and there's up to class 4, which are really quite dangerous if you don't use them correctly. And I think laser pens tend to range from class 1 to 2, depending on how powerful they are. But the lasers we use are a class 4, which are the most dangerous. And so you have to take extra precautions when you work with those. They have to be enclosed, and you have to wear protective goggles, because if you looked directly in that beam, you would be blinded. It would damage your eyes permanently. So there's things like that, but they do have things in common in that laser pens and the lasers we use emit generally one wavelength mainly. So they are one colour. And I'd say that's probably the biggest similarity between what we use and the laser pens that you use for your experiments.
Okay, that's really interesting. I wonder then, if we think back to the challenge with the diffraction grating, where we were when we shone the laser pen through the CD, diffracted the light into the 3 little spots. Is the distance between those spots, I'm sure lots of people are wondering, is the distance between those spots, what does that relate to in terms of, does that relate back to anything about the laser pen? Do we know?
It may well do, actually. I would say yes, it does. So there's a couple of factors that may be at play here. So the first factor is the actual colour of the laser pen itself, because different colours have different wavelengths, and that may have an effect. And also the difference, the distances between the actual tracks on the CD or the DVD itself could also have an effect. So depending on the colour of light that you shine at the CD and the distance between the tracks, that would affect the distance that you observe. And it would be a really interesting thing to do, perhaps as more people do these experiments, if we have what colour you used, whether it's red, green, blue, whatever it might be, and then if somehow we can work out what the distance is on the CD, maybe at the end we could put everybody's results together and look at how those different factors might affect the diffraction that you see.
Mm-hmm.
That would be awesome. And I'll point out to everyone listening that if you have tried the experiments and you want to feed back any of your results, you can absolutely do that. You just need to go onto the website, and there's a section on there that says celebrate your success, and it shows you how to go about letting us know how you've got on with the experiment. So you can send us pictures, which we can share in a place on the website, or we'll talk about it during the live Teams meeting. We would love to hear all about how you've got on with these experiments, because at the moment we have no idea how you've got on with the experiments. We know how we've got on with them because we've talked to each other, but we would be so happy to hear and find out how you've got on with the experiments and what sort of results you've gathered from those. So actually that point, Emily, is really, that would be really, really interesting to be able to gather all of that data together and see if we can find any trends and links and see what we can work out from it, and then tell you guys all about what it is that we've found from looking at all of that. That would be really, really exciting. So yeah, please do share. We would be really, really keen to see how you've got on with that. Right, did anybody want to add anything to that one, or should we move on to the next question? Right, another one that's come through. Somebody has said, how can I make the camera obscura picture better? So I guess like me and my makeshift picture, perhaps their picture didn't come out quite as well as they were hoping. Do we have any tips for making that camera obscura picture any better, judging what we know by what's happening in the science in there?
I mean, I know I've spoken a lot, but I did actually make one. So I don't know if you want me to kick off.
Yeah, go for it. Yeah.
So I might as well. I've saved the prop for this Teams meeting. So this is my effort here, made from a Sky Wi-Fi box, and so this was actually my second attempt at making one of these. So originally I had a smaller box that was very thin. It was just a snack box that I had, and I didn't have any success with that box at all. And I think there are a couple of reasons for that. Firstly, I think it was too narrow. So I think my head was blocking the light coming in, which is a definite problem. And the second problem was that the box was quite thin. So I think there was too much light coming into the box from at the outside. So then I thought I'll try putting it in an envelope and see if that made any difference, but I still couldn't see anything, and the screen was quite small as well, so that I think it's a combination of those factors. So then this was number 2, and you can see we've used the longer end to make the holes, so that eliminates the problem of your head being in the way. And the second thing that we found really helped was having a big contrast between the light in the room and the object that you're looking at. So I was trying to look out of the window that's just here, and didn't get anything, and that's because we've not had much sun here in the north of England for quite a while, so I couldn't get a well-resolved image. So what we did instead was to put the lamp on and look at the actual bulb in the lamp. Obviously don't look at the bulb directly because you'll do yourself some damage, but so we had the bulb in the small hole and we were looking through this larger hole, and we could see really clearly the text on the bulb and the image of the bulb, and I think that those pictures will go on the website as well. And it took us a while to get the right angle. There was a lot of this going on, a lot of different angles, and initially I couldn't see any image, but once you got the perspective correct, we actually got quite a good image. So in summary, my tips would be make sure the box is large enough, and try and get as much contrast as you can between the object and the light in the room. So make the room as dark as possible and the object as light as possible, and keep trying, because it's really cool when you get to see an image in just a cardboard box. So
it is really cool. Thank you, Emily. They're really, really helpful tips. I don't know if Nat or Abby, you had a chance to try to make a camera obscura, but I know that I had a go at making one, and I think that it's behind me, hidden somewhere in a pile of wedding stuff, so I'm not going to try and pull it out, because I might be there till next Christmas. But I also found, I was just sat at my desk, and I had it behind me. I was sort of facing the wall behind me, and I've got a big window in front of me here, and I was just trying to see if I could, one, see the windows, and then see if I could see anything outside the window. And I think the picture that's up on the website is the one that I took a while ago. And I just got sort of upside down trees and window panes, and you can just about tell that from the picture-ish. But yeah, I found that I had sort of similar maneuvering issues as Emily, and it wasn't working very well when it wasn't sunny outside. So I was kind of sat here doing work, but then every moment that the sun appeared behind the clouds, I was like, oh, it's camera obscura time, and I'd get it out and try to get a better picture. And at one point the sun did come out, and I think that was the best picture that I got. But I wonder whether it might be a thing that perhaps doesn't work outside then, if you need the contrast. I'm not sure. I didn't take it outside, but that might be something that we could do as that people at home could do to further experiment with their camera obscuras. So if you look at camera obscura on Google, some people have got the most amazing obscura images. I've seen some pictures of people making their room a camera obscura, and they have a little tiny pinhole in the window, and then their entire room is an upside down image of what's outside. It's mental. Really, really impressive. Now, I'm not suggesting that you go and get loads of black paper and board up all of your windows, but it did look really impressive. One other tip that I would suggest, if you're really struggling to see that image inside your camera obscura, one tip that somebody mentioned to me that I didn't do with my box, but perhaps might be a useful tip, is on the side where you're making your holes in your box, for your pinhole, if you put a little bit of tin foil behind it and then poke through a needle, that makes that hole even smaller, which means that I think it makes the image a little bit sharper. So perhaps that might be something else that people could try if they're struggling to get an image. So hopefully we've answered that question for whoever posted. And if you haven't had a chance to make your camera obscura yet, I would definitely recommend it. It was definitely, I think it took me sort of half an hour, 20, well, not even that long, maybe 20 minutes of faffing with a box to make it, and then hours of fun afterwards trying to see the picture inside. So yeah, definitely recommend that you have a go at that if you've not had a go at it. And you do literally just need a box, piece of paper, scissors, tape, and that's it. And you can also have hours of fun. Right, for loads of questions still coming through. Right. Oh, okay. So somebody has said, how do lasers apply into experiments? So does anybody want to talk about how lasers apply into any experiments that you are doing in the lab?
As in, how do we use them, perhaps? How?
I think so. They've just said, how do lasers apply into experiments? So I think, yeah, how are you using them in experiments? What are you using them for?
So, like I was saying, the laser in our lab looks like a box, and there's a light beam coming out, just like as if it was a laser pen. There's a beam, and then we use lots and lots and lots of mirrors to get that beam to where we want it. So we put a mirror in the way, beam comes in, goes out, and we use lots of mirrors. So you can imagine if you watched Indiana Jones, you know, with the mirrors that the light goes all over. That's kind of what we're doing. And eventually at the end we have our sample, which is just another bit of a glass, and we sandwich some liquid in between two bits of glass, and the beam comes in and hits it. And that's our experiment. We just get the laser hitting the sample, and we study that. Of course, then we measure the light that comes after the sample, and there's lots of detectors and computers and things like that, so that we can see how the light is changing as it goes through the sample, how the light is changing. So that's how we use the laser in the experiments. I think that explains it somehow.
Yeah, I think that explains it for me. Hopefully it explains it for the person that was asking. Does anybody else use lasers in a different way, or is it similar for both you, Abby, and Emily?
Yeah, it's similar for us, but I was just going to add, that's the way we use lasers, but there's loads of different applications that we can use the lasers for. So you could study any sample and look at how the laser and the light interacts with the sample. And these can have applications in sunscreens, which is what we're all interested in, but also electronics, solar cells, medicines even. So there's loads of different applications that we can then use our lasers for. So it just shows how versatile lasers are and can be.
Awesome. Is it the same for you, Emily?
Yeah, it's very similar for me too. So I personally have been studying individual ingredients in a sunscreen with the laser to find out similarly how the light interacts with those ingredients, and from that we can determine whether they're safe to include in a sunscreen or whether we can find better alternatives. So that's how I use them personally.
Excellent. Leading on from that, we've actually had a couple of questions about sunscreen specifically, sort of linking back to the UV beads experiment. And some people have said, and I think we might be able to answer this. So people have said, how are sunscreens damaging the coral reef? So do we know how that works and sort of why that's happening, what's causing that? Is that something we want to think about for a minute?
So I don't know exactly what it does, but essentially, so the corals, you know, they've got little animals, they're live beings, right? And the only thing that happens is that the sunscreens, the things that are inside that are used to protect us from the light, they're chemicals, and some of them are toxic to these little animals that live in the coral reefs. So it's just a case of toxicity, the same way that some chemicals are toxic to us humans. Some of the chemicals that are in the sunscreens are toxic to the corals. It's just a case of, yeah, that's it. They're just toxic to them. I don't know exactly the biological mechanism of action for all of this, but the corals just die when they come in contact with these chemicals.
Is it the chemicals themselves, or is it like degradation products? This is more of a question than an answer, but I'm just wondering.
A bit of both, I think, a bit of both. But I think one of the worst ones for the corals is octocrylene, if I'm not mistaken. And in terms of so some UV filters, some of these sunscreen ingredients, when they absorb light, the molecule itself, it breaks apart with the excess energy. But octocrylene doesn't do that. It stays together, and yet that octocrylene is toxic to the corals. So I think there will be a combination. It's either the sunscreen ingredients themselves or the bits that they break apart into once they absorb the lights going. I think it's a bit of both.
Yeah. So what's that? Is that octocrylene? Did you say, Nat? That's what we need to look out for on the ingredients list to make sure that we're not using sunscreens with that inside.
Yes, octocrylene. And if you go to Hawaii, I think it's from next year, if you have a sunscreen bottle that has octocrylene, you can't go to the beach because they're banning it.
Well, that's good, really, isn't it?
And there's more places around the world that I have no idea how they're thinking about policing it. But there's plenty of places, and there's places in the world where, especially like Virgin Islands and places, remote places that are very sensitive, they will not let you come in with any sunscreen whatsoever, and you are told before your excursion there, do not apply sunscreen. I mean, bring a shirt.
Wow.
That would not bode well for me.
I was gonna say, me neither. Sunburn time. So I guess, what other questions have we got? This actually is a great question, which sort of leads on exactly from what we were just talking about, which is very fortuitous timing. Somebody said, what alternatives are there to sunscreens which are damaging the coral reef, apart from, just wearing a shirt?
So before, because I think Abby really is doing a lot of work that relates to this, but I will just say, for now, the most effective thing to do is to not go out in the sun when it's at its strongest. Love your skin tone, whichever one it is, and wear a shirt, cover your skin, seek the shadow, wear your hats, all of those things that are boring but are the most effective way of protection, and they are all recommended above sunscreen. So, but we can make sunscreens better by
finding new UV filters, studying new UV filters. Especially, so my research is all about studying new UV filters that are inspired by nature, because nature's been around much longer than us and has developed its own photoprotective families, which are much, much better than what we can produce in a lab. So The hope is that they will be safer because they already exist in nature. But watch this space, I'm sure. We'll get there eventually.
Well, that's really great to know that research is actively going into fixing this problem, because whilst Nat has said that seek the shadow, I love that phrase, I'm going to use that phrase. We should seek the shadow above all else. It's I mean, are people actually going to follow that? The sunscreens, I don't think that we're going to abandon sunscreens anytime soon, and so it's really great to know that this research is happening to develop sunscreens which won't damage the coral reefs. I mean, if you've seen Blue Planet, then, or Our Planet, or Planet Earth, or anything with the god David Attenborough commentating, then you will have seen the absolutely just devastating effects. It's not all caused by sunscreens, obviously, but it's a contributing factor. And so it's very reassuring to know, I'm sure, to everyone listening, that research is actively going into fixing at least this one aspect to save the coral reefs.
I mean, and the good news is that we found some pretty good candidates, right? I mean, there's a lot of work going on in the research group at Warwick, and there's some molecules that we found that are really good, and we are now having the worry as well. Whenever we study a molecule, we don't just say this is a good sunscreen in terms of how it interacts with the light. We also try to see if it is toxic to like living cells and things, to start having an understanding if they would be good in an actual sunscreen final product. And we already found a couple of things that are really, really promising, and that could be really, really good. So, I think it's promising. That's the good news.
That's really reassuring, that I'm sure, to everyone listening, including me, because I'm quite traumatized after watching the bleaching of the coral reef on Blue Planet. So that's really good to know. Right, let's have a look at some more of the questions that are coming through. Right, I've had a couple of people ask me, what is a diffraction grating? Can anybody answer this one for me? What is a diffraction grating?
I can go.
All right.
A diffraction grating, when we say grating, it's, now I have it in my mind. Now, how am I going to say it with words? Hang on. Do you know what? I'm going to wait.
It's one of those things that's very difficult to describe, but easy to draw. Yeah.
Yes. Right. Science time. You can't do science if you're not drawing things.
Brilliant.
Right. So a diffraction grating is something that looks kind of like this. So it's got a surface that has these like teeth, if you want to call it that. And then what happens is, right, hang on. That's light coming in. Yeah, the light comes in. And then because it's got the different teeth, the teeth sort of send light different ways, so it disperses it. I mean, this is not, so it's not quite right. It comes in and it hits these teeth, and that makes the light travel in different ways. So if your light has many colors, when it hits those little teeth, the different colors want to go different ways, and so it sort of expands the light, it separates the light. But you can also have gratings that in a similar way act the opposite way. So many colors come in, and then the teeth make the light travel in such a way that it sort of closes it and combines all the colors again. So it's a different way to achieve the same thing as a prism. If anyone has ever seen, I don't know, people watching maybe don't know about Pink Floyd. I don't know if they do or not. But a prism is just, it's just a crystal that when white light goes through, a rainbow comes out. And so it's that same sort of separation, but with a diffraction grating, you achieve the same thing, but with this physical structure that are these little teeth. I hope that answers the question.
I think that's a really good explanation.
And maybe we'll get some people after this going to search Pink Floyd and listen to Pink Floyd, which I think it's a win.
Oh, yeah, maybe that would be a bonus. Awesome. Thank you, Nat, and for your amazing diagrams. That's really, really helpful. Oh, following on from that, somebody said, what might we use a diffraction grating for? So, yes, that's how it works, and it's sort of dispersing the light by sort of bouncing off the teeth. But what would we use that for?
Shall I continue, or does someone else?
If you know, or if someone else wants to jump in, that's fine.
So again, it depends on what you are trying to do, but sometimes, like we were saying, lasers emit light of just one color, and sometimes you want more colors. So sometimes you want to disperse that one color into more of them. So, I mean, that's not quite right. Let me rephrase that. Sometimes we need, if you have white light and you want all the colors, you can use a diffraction grating. But sometimes what you need to do is to compress the light. And that really depends on what you're trying to do with your experiments. Sometimes you need one color, sometimes you need more colors. And also, and here's where it gets a little bit weird, we can also disperse and compress in terms of time and laser pulses. So lasers work in pulses of light, and sometimes you need really fast pulses, and sometimes you need slower pulses. So what you can do is you can use these dispersion gratings to sort of tune that pulse as well. So there's many different reasons that you can use it for, but essentially they are used for what we call temporal or spectral dispersion or compression. So in terms of color or how fast they blink, you can either disperse or compress. That's what you use it for. And that depends what you want to do with your experiment. I hope that answers without being too complicated, because laser physics can be a mind-blowing field of science. So
wow, that was super interesting. Thank you, Nat. That was a really good explanation. Does anybody want to add anything to that, or do we think Nat's covered it?
I thought that was pretty good, Nat, to be honest.
Yeah,
that was
I agree.
impressive.
Really impressive. Thank you, Nat. Really, really good. Right, what else have we got? Oh, here's an interesting one. So we're thinking back to sunscreens, and some people may have seen the effects of this doing the experiment, although someone's asked. They've said, is it likely that different brands of sunscreens with the same SPF number might offer different levels of protection, or should they all be the same? Is there like I guess they're trying to say, is there like a standard at which they all have to adhere to be classed as SPF 30, for example? Or do we see variations between them? Do you guys know?
Yes, is the short answer to that question. Yes, there are very detailed guidelines on what is labelled, for example, SPF 15, SPF 30, SPF 50, etc. And those are quite worldwide implemented, and you can do it in a couple of ways, but the main way that it's done at the moment is actually with volunteers. So people go and they will be irradiated with the UV light, and they'll have the sunscreen applied as well, and they'll measure the difference in how long it takes for their skin to burn. And that is the best way that we have at the moment of determining how good the sunscreen is. There are ways you can do it, what we call in vitro. So that means not on a person. It means using a model. So as Nat was talking about the plates earlier and using a solar simulator, that's the sort of thing that we're talking about. But getting that number reliable is also challenging. So you get variation with human volunteers and variation with the in vitro methods as well. But I think the guidelines are probably stricter for the human volunteers, and that's how they determine the number. So the higher the number, the greater the protection. But there's also other things to consider as well when you're looking at a sunscreen and how protective it is. So SPF only relates to one section of the UV light that the sun emits. It's only one portion of it. The other portion in the UK is measured by, you may have seen the stars on the bottle. And up until I think about 10 years ago, they didn't think that these wavelengths was harmful, but now they know that they are. And so the higher the stars, the more protective it is against what we call UVA radiation, which is also emitted by the sun. And there's definitely been a shift in the last few years on trying to get the protection as uniform as possible. And what I mean by that is getting it so that it's like wearing a piece of clothing, so you get equal protection from all the wavelengths of light. So if it's got a high SPF and a high star rating, that's the best protection you can get, I would say. And I know the company that Nat works for now do a lot of work in that area and actually carry out those tests. So if you've got any stories about that, Nat, I'm sure that they'd love to hear them.
Yeah, I was just going to say about how difficult it is. So you're definitely right, Emily, that the value of SPF that you see on the bottles comes from a measurement on actual skin of actual people. So some people do volunteer to essentially get a bit of sunburn so that these values can be calculated. And there's a big push, and this is in all of Europe, and for all types of science, there's always a big push to test things not on humans, but to be able to do it in vitro, so in models, so that we don't need to be, burning people to get this value. The problem is that I found, when you apply sunscreen to your skin, some of the sunscreen actually gets absorbed and is not at the surface anymore. So that's a really difficult thing to imitate in the lab. So the value that you measure when we use our plastic plates and we put some sunscreen and we test it, the SPF that we get there is always very different to what is measured on the skin, because you have this effect of absorption and everything that is really difficult to mimic. So that's one thing. There's that difficulty. The other thing I was going to say is that sometimes I think people think about SPF as a linear thing. And what I mean by that is you think if SPF 50 gives me some protection, SPF 100 is going to give me double that protection. But that's not right, because the way the SPF value is calculated, it means that the higher you go, the less difference there is. So I don't want to be lying to you with the numbers, but I think it's something like SPF 50 gives you about 97% protection, and SPF 100 gives you 98%. Don't quote me on these exact numbers, but what I'm trying to say is the difference when you get to really high SPF, the difference is very small. So if someone is trying to charge you £20 more for an SPF 100, it's not worth it. It's what I'm trying to say.
That's really interesting to know. On that point, somebody said, is it dangerous for sunscreens to be absorbed into the skin?
At the current, one thing, the sunscreens are tested with 2 milligrams per centimeter squared of skin, which is, I think it's two tablespoons for 2 teaspoons for a piece of skin like that. I mean, it's loads of sunscreen. We never apply that much, never, which also should remind you that the SPF that it's in there, it's measured for a lot more sunscreen that people tend to apply, a lot more. So when we test for the toxicity of the sunscreen and things, we are testing for a much higher amount of sunscreen. And it is very rigorous. I mean, sunscreens fall into that bit where it's not quite pharmaceutical, it's not quite cosmetic, but the standards are very rigorous in terms of toxicity and everything. So they're always being reviewed as well. So there's active reviews on the safety of these things. So if it's out there in the market and you bought it from a supermarket, especially within the European Union or in the UK, it's it's safe. It does go into the skin, but it does not harm you. And again, it's been tested for a lot more sunscreen than you're actually going to be using. So they are safe.
That's good to know. Yeah, because it would be unfortunate if they were dangerous and we were putting them on to protect ourselves. So it's really good to know that they're not dangerous, even though they're being absorbed into the skin and they're going under such rigorous testing. Following on from this, somebody said, what sorts of things in nature are we investigating as replacements for current sunscreens? So sort of where in nature are they found? And I think I'm looking at Abby for this one.
Yeah. So Emily's also done some work on this, but we've taken, I guess, the 2 different directions. So I look at a family of molecules that microorganisms synthesize. So this is bacteria, algae, and fungi. And then the other side is what plants synthesize, and that's the stuff that Emily has taken a look at. So yeah, lots of different organisms in nature do also need this protection in order to survive.
Can I add a really fun one?
Of course, yes.
That we have not looked at, but we had a lot of laughs in the office thinking about.
I think I know what you're going to say.
Did you know that hippos, they have this red sweat, and that's where they get their photo protection from? So if you go on Google and look for hippo red sweat, they segregate this red liquid all over their skin, which has I can't remember the name of the molecule, but that's where they have the photo protection. Oh, wow. And no joke, at some point we thought about testing this, but we couldn't find this molecule just sold online. So we actually contacted a zoo to try and get some of this red sweat from a hippo. It ended up not happening. I think the people from the zoo might be like, why do you want hippo sweat? But I mean, the avenue for research is there. That's another place where we could get their sunscreens. Who knows? Who knows?
Oh dear, next thing we know, there's going to be research groups cropping up investigating red-sweated hippo red sweat. Yeah. Stealing your idea. That's really funny. There could be other animals out there doing similarly weird and wonderful things that we hadn't thought about. So that's really interesting to know, because I guess it means that, you know, there are loads of potentials that we could be looking at. We may not even know about them yet, but thank you for adding that. Now that's really funny. Oh, Emily, is there anything that you wanted to add about that? So where in nature are these replacements for current sunscreens found?
Yeah, it's just been really nice to reminisce about that, because yeah, that was a source of, yeah, it was brilliant at the time. and it was really, everyone was so excited about it. But yeah, the zoo were not as excited, I don't think. But yeah, so just to add on to what Abby said about my work on nature-based sunscreens. So whereas Abby's looking at the microorganism side, I was looking at the plant leaf side. And there's a particular pigment in the leaf surface that protects it from UV and stops it getting burnt, just like melanin, it's called, the pigment in human skin that does that. And I was looking at a variation upon this because sometimes we might want to change the plant leaf version, because that was designed for a leaf, and we want to design it for a sunscreen. So we might need different chemical properties. So we might change it slightly. And so I looked upon a variation where we changed the structure slightly, and yeah, it gave some really interesting and promising results. So watch this space on that one.
So yeah, that's really interesting. So looking at all areas, really, plants, microorganisms. That's really exciting. Right, I think that's going to be all the time that we've got today for your questions. I hope that we answered most of them. If there are any that we've missed, or if you have any throughout the rest of the week, please feel free to post them over the week. We'll keep an eye on the Slido on the website and answer any questions throughout the week as and when they come through. Next week, we're going to be talking all about sort of the experiences and opportunities that we've had, maybe outside of our chemistry degrees, whilst we've been at university. So we've all got a few little anecdotes up our sleeves about opportunities and experiences that we've had whilst doing chemistry degrees, to sort of show that, you know, whilst it is really hard work and very rewarding, there is still time to enjoy the university experience, and all of the opportunities that brings with it too. So we're going to talk about that a little bit more next week and answer any of your questions about that aspect of studying chemistry at university too. But otherwise, I think we'll wrap it up there. It's been a really great session. Thank you all so much for all of your questions and for listening. And we will be back with you next Friday at 4 p.m. for our last Women in Chemistry meeting, Light Up, in April with all of you. So thanks very much again from all of us here with you today, and we'll see you next Friday. So bye.
Bye.